So hi everyone, my name is Benjamin Pasquier, and with my colleague Houda Chabbi, I am excited to present our research on a comparative study of deep learning models for granulometry image-based estimation of concrete aggregate. Sorry for the long title. This work is conducted under the Institute of Artificial Intelligence and Complex Systems, in short iCoSys, at the School of Engineering and Architecture of Fribourg in Switzerland. As you may know, the production of concrete is relatively polluting, and today we would like to be able to facilitate the use of recycled aggregates in it. In Switzerland, 25% of aggregates used for concrete production can come from demolition, but only 25% of demolition aggregates are actually used. This is partly because the use of recycled material requires greater precision in the mix when producing concrete. So this is why the iTech Institute of our same school launched two projects carried out jointly with our institute to respond to this problem. So these two projects aim to use AI, more specifically machine learning and deep learning techniques, to predict concrete final properties and thus adapt production in real time. On these final properties, the granulometry plays an important role and should therefore be considered. It is normally obtained manually using sieves, which can be relatively time-consuming. So automatic prediction of this would make it easier and quicker to adapt the concrete receipt to obtain better final performance. So therefore, our research focuses on the use of deep learning techniques to obtain this prediction, which would be the starting point of our final pipeline. So our problem consists of predicting the particle size, so the granulometry, from images of aggregates. This problem can actually be formulated in two different ways, either as a classification problem, where we try to predict the particle size class, typically according to the German standard DIN 1045, or as regression problems where each percentage of the grain size considered must be predicted. In our research, we take these two formulations into account, although the end goal is to solve a regression problems where the prediction at the end is more accurate. As we want to use a deep learning model to predict granulometry, we focused on existing models. So two choices are available to us. Either we use a custom model for our specific task, if it exists, or we use pre-trained models which we fine-tune on the same task. We are a bit lucky here because there is a model that was created specifically for this task called the AgNet, which is based on a convolutional model. We will then be able to compare it to other models which are pre-trained on the very well-known ImageNet dataset, namely ResNet, MobileNet, which are both CNN-based, and a vision transformer that we will call VIT for short. So the pre-trained models are fine-tuned using the transfer learning principle, where the feature extraction layers are frozen and the final classification layer is replaced and retrained on new data. In this case, the goal is precisely to take advantage of everything that these models have learned to extract meaningful features on the images. About the data used to train these models, we used two data sets which were published by the same authors of the AgNet model, thank to them by the way, and also a data set which we put together ourselves. So the first public dataset, named Visual Granulometry, is built for classification towards classes of the DIN 1045 standard, while the second one is for regression towards the percentages of the bin grain sizes considered, for example, from 1 millimeter to 2 millimeter. Unfortunately, our dataset contains relatively different granulometries than the public datasets. So for classification, we assign each of our granulometry to the closest DIN 1045 class using the least squares method. Here you can see the dashed lines represent our granulometries, while the solid lines represent the DIN classes. So the four chosen models are evaluated according to the same procedure. So for regression, only the two best models on the classification task are considered. So about this procedure, the data is first separated into a training, validation, and test set in a very classic way. The validation set is used to test a large amount of possible hyperparameter and data augmentation combinations, and thus create the best performing model possible. Once all the models are trained, they are evaluated on the test set, and their performance is compared according to the defined metrics. We only use actually the two public data sets for training the selected models. We do this firstly because the quality of our data is not as good as that of the public data sets, but also because this allows us to evaluate the generalization of the models on images of aggregates with very different granulometries from the training ones. Note that the evaluation is also carried out on a held out part of the public data sets. Concerning the metrics, we use the standard accuracy metrics for classification and the mean absolute error and root mean square error metrics for regression. So first about the classification results, it shows that the fine-tuned VIT model obtains the best performance with a very high accuracy on both public data set and our data set. The Aggregate neural network also performs very well on the visual granulometry data set, confirming the results reported by their authors. It is also interesting to note that all models show poor performance on our own data. This confirms that our granulometries are maybe too far from that of the DIN 1045 standards, and therefore from the training data. In fact, as you can see, the confusion metrics shows that each sample is almost systematically classified in the same class. Still, we can state that the two best models on this first task are VIT and Aggregate, and the regression results actually will be more interesting about them. So we therefore evaluate these two models on the regression task. If we average the errors of over all grain size beans, we see that once again the fine-tuned VIT model shows better performance on both data sets with an average absolute error of 0.58 compared to 1.15, which is almost the half. So both models appear to have more difficulty predicting proportions of certain grain sizes, particularly from 4 to 31.5 millimeters, showing that some sizes are more difficult to differentiate than others. On our data sets, you can see that the errors still remain very high in both cases, showing that the models were not trained on enough varied data to generalize well. Visually, we realize that then even in the worst case, the grading curve predicted on the deep granulometry dataset is very close to ground truth. This is not the case on our dataset, although the quality of the best prediction remains encouraging, knowing that this is a granulometry that the model has never seen. In a real setup, many images of the same mixture of aggregates and therefore of the same granulometry would be taken. So it is therefore interesting to visualize the average of the predictions made by the model on the images of aggregates that follow the same granulometry. By doing this, even the worst average grading curve is very good on the deep granulometry data set, as you can see on the left. On our data set, the prediction is still not perfect, but we managed to reduce the error from 0.13 that we had on the previous slide to 0.11 now. So with these encouraging results, I would finally like to conclude this presentation. Our experiments therefore showed that fine-tuning pre-trained CNNs did not seem to outperform a neural network specifically designed for predicting aggregate granulometry from images. However, fine-tuning a model based on new vision transformers is a promising alternative approach and can even outperform the custom model. Also, the results on our data on our data set show that VIT has superior generalization capabilities, although it is not yet optimal. This is why in the future our research will focus on two main axes. The first axis is the enhancement of our own data set, meaning the collection of new images to cover a greater diversity of grain sizes, but also the balancing of our data set with the aim of also using it for training a model, because for now it is a bit imbalanced. So, and precisely, in a second time, we would like to be able to improve the generalization capabilities of VIT by using part of our data set for training, either by fine-tuning the current model on this subset of data, or by reapplying transfer learning from scratch, as we did in this work. So here we come to the end of this presentation. So on behalf of Houda, my co-authors, and myself, I would like to thank you for your attention. Of course, if you have any questions, I remain available and will be happy to answer you by email. Thank you.